Practice exam 10 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. We drop a baseball from rest. The terminal velocity of a baseball in air is about 42.5 meters per second. So the ball's going to accelerate quickly initially, and then pretty soon the drag force is going to increase, and speed's going to level off at about 42.5 meters per second. Part A asked for the acceleration of the baseball as soon as it is released. So let's start there. To get the rate of change of speed, we need a good tangent line at 0. So the change in speed is the rise, and the change in time is the run, and the change in speed over the change in time is the linear acceleration. So there's a good tangent line. The rise is the whole vertical axis, which is 45 meters per second. The run goes maybe 4.5 seconds. So the slope is 45 meters per second divided by 4.5 seconds, which is about 10 meters per second every second. The acceleration due to gravity near the surface of the Earth is 9.8 meters per second every second. So we're happy with that result. Part B. Estimate the acceleration of the baseball at 10 seconds with a good tangent line. So let's first identify the point. There it is. Now we can draw a good tangent line in, and then the rise looks like 28.5 to 45, the top of the graph. That's 16.5 meters per second. And the run, about 17 seconds, right here, 17 seconds. So the slope is about 1. We got a little bit less than 1 meters per second every second. So the acceleration is not that big after 10 seconds because the air drag is significant. On to part C. There's the normal equation of the line that relates v to t. That's what the graph is. Take the derivative of both sides of this equation and solve for dv dt. Substitute in t equals 0 and t equals 10 seconds. Compare the results to your answers in part A and part B, which was the tangent lines at 0 and 10 seconds. So we're going to change t and get the change in v. So here's the equation. We change t by dt, and v changes by dv. That's differential calculus. And to make things easier, we're not going to carry this 4.33 seconds through all this math we're about to do, so let's just call that tau. The Greek letter tau, so now we have this. We don't have to copy that 4.33 seconds every time. We're just going to write tau. There's our equation. We can manipulate the exponent like this. This times this is e to the this minus that. That's how you combine exponents. Subtract the original v from both sides, and we're just going to subtract the normal equation right here. There it is. There's the normal equation with the tau in it, and that's how we got rid of the v. So there's what we have above, and we subtracted v from both sides. Now we can mess with this a little bit. We have 42.5 meters per second times positive 1. We have minus 42.5 meters per second by negative 1. So those two terms go away. And we have this. And now we have 42.5 meters per second times e to the minus t over tau, and we have 42.5 meters per second e to the minus t over tau right here. And there's a negative sign out front. So I'm going to factor this whole thing out like this. So the 1 is from here, and the minus e to the minus dt over tau is right here, and there's the negative sign right here. We have e to the minus dt over tau, and we have to know what that is. From the infinite series for e to the x, we know that e to the x is 1 plus x, exactly, when x is infinitesimal. So we can substitute in for x when 1 plus x for e to the x when x is infinitesimal. And here it is. It's minus dt over tau. So we have this, and we know that e to the minus x is 1 plus x when x is infinitesimal, and there it is. There's our x minus dt over tau. So we're going to substitute this term in right here. So 1 minus this thing right here. The 1's go away. We have 1 minus 1, and that reduces to this. And we're going to put the 4.33 seconds back in for tau. So we have a tau on the bottom over here, which is right here. And we have a tau on the bottom of the exponent, which is right here. And then we can put the dt on the other side to get the slope. Combine the first two constants. 42.5 meters per second divided by 4.33 seconds. That's an acceleration, and it turned out to be 9.8 meters per second squared. There is our slope at any t. Any t. There's the slope at any t. Plug in t right here. When t equals 0, e to the 0 is 1. So at time equals 0, you get 9.8 meters per second squared, which is what we expected, the acceleration due to gravity, as soon as the ball is released. So now we can plug in 10 seconds. So we plug in 10 seconds, we get e to the minus 10 seconds over 4.33 seconds, which is about e to the minus 2.5. E to the minus 2.31 times 9.8 meters per second squared. That's 0.97 meters per second squared, and that was luckily, surprisingly, exactly what we got, the two significant digits for our tangent line in part B. You would expect it to be that good. Finally, part D, write an expression for the infinitesimal distance, dx, the baseball falls in a time from 12 seconds to 12 seconds plus dt. Needed expression for dx. Great opportunity to develop a fundamental understanding of what differential calculus is all about. So the normal equation that gives the speed of the ball at any time t is this. This is given. We can get the speed of the ball at any time t. If we want to know how far the ball travels in a time dt, the only thing we need to know is the speed. The acceleration is completely irrelevant because the speed of the ball can't change in an infinitesimal time. The speed is defined as dx dt. There is no acceleration in this equation. It doesn't matter whether the object is accelerating or not. The only thing we need is the speed. So from the normal equation, we can write this. Instead of the v, we can put in dx dt. Now we can solve for dx. And we can plug in 12 seconds. Plugged it into the exponent. We have e to the minus 2.771. And we do the calculation, and we get 39.5 meters per second dt. And that's the speed of the object at 12 seconds, the ball. And we can check it. Well, we can look at it and try to estimate it from the graph. How fast is it going at 12 seconds? Oh man, it looks like it's going 40, almost 40. Right? Here's the dashed line right through 12 seconds, a little bit less than 40. And you know what? It looks like 39.8 to me. So from the graph, we can just write down dx is 39.8 meters per second dt. Makes sense, hopefully. That's problem 2.